Unit number 2, transistor and operational amplifier. In this unit, we have to study the diodes or devices, circuits that are useful in amplification or controlling the signals through the circuits. Okay. Performing various operations such as summation of two signals or differentiation or integration of two signals. Yeah, any signal. Okay, such circuits are analog circuits that can be designed or implemented with the help of device called transistor that we have to learn. Yeah, so we have to learn BJT transistor, that is bipolar junction transistor, then its characteristics parameters, then a very important yeah topic of this BJT is DC operating point, DC operating condition, where that particular transistor had to operate within a particular values of voltage and current for successful operation. We have to again learn how this transistor can be used as switches are used to form logic gates, and gate, or gate, nor gate. And with the help of those logic gates, we design different digital circuits, adder circuit, subtractor circuit, multiplying circuit, all this, which is the what basic building blocks of a particular microprocessor, microcontroller, or computer hardware. Then we have to study the metal oxide semiconductor field effect transistor. And using all those transistors, we have to design a amplifier called operational amplifier. Yeah, BJT is bipolar junction transistor. Okay, it is having two diodes connected in device, okay, that we have to study. And in this device, and the current that is flowing is because of the holes and electrons both. So that's why it's called bipolar junction transistor. It has three terminals: collector, emitter, and base. And base is used to provide the control signal to this device, and then collector is the point where we get the output. And whatever the signal we apply at the base, it get amplified at collector. That we have to use as an amplifier circuit. Yeah. Okay. So from applying a very small power signal at the order of current of microampere or milliampere, we can uh, get a certain output with same variation of with same frequency, but a greater amplitude and greater current at the output of this collector. Yeah. So basically, this happens through a phenomena or a term we call it the transfer of resistor. Okay, transfer of resistor. So we have to pass the current from lower resistance to higher resistance, and because of this, right? Because of this, we get higher voltage at higher resistance, right? As current is generated at lower resistance, and because of lower resistance, at that resistance we had lower voltage, and when it goes to higher resistance path, because of the higher resistance, the same current when multiplied by that particular um, yeah resistance, right, we will get higher voltage, right? So there are two types of BJTs, NPN and PNP. Okay, that will we see in more detail. This is the structure of a particular NPN transistor. Okay, so what we have, two N type materials. One is this and this, and within this we use a P type material sandwich between this N type material. Okay, and we have named all those terminals as yeah, this larger region of N type material is called collector, while this middle region is what called base region, and this third one is called emitter. Yeah. So these all are what p n junction regions, right? So whenever two p and n regions are joined together at the surface of their contact, right, there is a formation what depletion layer or PN junction, right? So in this device, we find two junctions, two PN junction. One is between this base terminal, and one is between this emitter, right? This base and emitter region where this junction is formed. This called emitter base junction. This is basically similar to PN junction diode region, right? PN junction, right? And this one is the second junction that is formed within this base and this collector region, P and N. So this is what collector base junction JC. Okay, it is also similar to PN junction region that we have seen in PN junction diodes, right? So as we controlled this PN junction diode on and off by applying the forward voltage and reverse voltage, the same voltage conditions we have to apply, and we have to turn on and turn off these junctions, right? And because of this, there is going to be what variation in the resistance at this region, because we are aware that whenever PN junction is forward bias, right? Suppose this PN junction is forward bias, so this region will have very least resistance, and because of that, current will flow through this PN junction, right? And suppose if the PN junction is reverse bias, right? Yes, then what is happening? The that particular depletion layer, the depletion region of PN junction is going to offer a very huge resistance, so that no current is going to flow. Okay, these things we have learned in PN junction diode also, right? PN junction diode, yeah. So same principle we are going to use in this device, but we are going to control the amount of resistance by applying the whatever the voltage or the current that is going to be applied to this terminals, base, emitter, and collector. Yeah. So what will happen whenever the current flows within this device? So it is going to vary. It is going to get some variation in resistance. So emitter is a region which is going to emit the charges, majority of charges. Yeah. Then base is a region where smaller amount of charges from emitter region we are going to recombine, and while remaining most of the charges has to be collected at this collector region. So charges is moving from this junction J, emitter base junction, then to this junction collector base junction, and then to this collector. So during this flow of charges, or we can say uh, whatever the current is going to flow, current is going to flow from opposite direction, right? If charges are moving from this emitter to collector, then current is going to flow from what collector to emitter. Okay, so this is how current is going to flow. But this whatever the current that is going to flow, that has to be affected by this junction, right? Junction collector base junction and emitter base junction by varying the resistance. And how we can vary this resistance? We have input right here, a base terminal, right? This base terminal we will apply a certain biasing, means certain voltage along this terminal, and because of that because of that these junctions are going to be affected, right? Because of that, the depletion layer of this junction are going to be affected, conductivity is going to be affected, so the resistance is going to be affected, and because of this the resistance is going to be vary, and that we have to do our control with the help of the voltage or the current that we are going to apply at the base terminal. And because of the variation that is happening between these regions, emitter based junction and the collector based junction, they are going to vary, right? And so the resistance is going to vary. So we will see that when the charges are flowing right from this emitter to collector, right? So they find um, they find a certain path where the resistance is increasing from this emitter to collector, right? So charges are offering some lower resistance here and much higher resistance there. So we can say they are when these electrons or whatever the charge carriers are flowing, they are getting some transition from lower resistance to higher resistance. So that's which is why this device is called transistor. Okay, so the current which the that current is going to flow from what, collector to emitter. Remember, charges flows from emitter to collector, while current correct yeah the current is going to flow from what, collector to emitter. Okay, so we have given this device a symbol like this. Okay, so these there are three lines. One, this is base, this is collector, this is emitter. So there is an arrow indicating the flow of current, right? The current flows from what, collector to emitter. So this the arrow indicates this is a NPN device. Where in NPN device, current will flow from collector to emitter, while this base is going to control the current. Yeah, what is the current flowing through this device, right? So this is the basic construction, right? And when it comes to the size of these regions, right? So what we see, the base is of very little width. Base is going to have a very little width, and then this emitter region is going to have more width. And as compared to emitter region, collector region is going to have again more width. Okay, so there is a very minute width of base, then a greater width of emitter region, and again more greater width of this collector region. Okay, and of course all those regions are doped, or they are going to have some concentration of impurities, right? That is concentration of how much amount of charges this region are going to have, right? So the concentration is also um, here varied for the required application, right? So how this concentration is here. The base is going to have very least concentration, very least doping. Then collector will have a certain moderate doping, right? And a greater doping or greater concentration of charges will be present in the emitter region. Okay, so these things we have to remember. Yeah, base is going to have very lower concentration of doping. Then collector will have a moderate doping, means greater than P, and again more greater than collector. uh, Emitter will have a more greater concentration of doping. Okay, or we can say emitter has the highest doping, and then collector is a lower doping as compared to emitter, and base is going to have very least doping of concentration, right? So this is what the doping concentration is going to vary within these regions. And yeah, now when it comes to the size, it is different, right? A very smaller section is what, base region, very minute width, micron, very smaller micron, 1 micron width. And then the emitter is going to have a larger width, and then that of collector is going to have very larger width as compared to emitter. So why we have to do all these things, right? So what we have to do, as we have to mm, make a path, right, where the charges are to be moved from lower uh, resistance to higher resistance, right? So for that purpose, so yeah, for that purpose, we have done all those things, right? So yeah, what we expect is that we have to control the maximum charges or maximum current, right? So what is happening? Emitter, okay, emitter is going to emit the charges, right? Emitter is going to emit the charges, and whatever the charges are emitted, they will go into this collector, right? At the same time, whenever the charges are moving toward this collector, they are passing through what base region, right? So smaller amount of charges are going to recombinate with these holes in this base region, means the electrons that are present or the charges that are present in this emitter region are going to recombinate with the charges, minority charges, or the what are the charges present in the base region, right? And let us consider there are 0.01 fraction of those charges generated by emitter are going to recombinate, while remaining 0.99% of the charges are going to what collected at this collector, right? Okay, so collector, yeah, so for that purpose, right, for the collector to receive the maximum number of charges, means 99%, and only 0.1% of the charges should be recombinant with these charges present in the base. That is why the doping concentration of base region is made very, very low, very, very low, so that only 0.1% of charges are going to be recombinant here. Means this width is going to be very, very small, that very lesser number of charges are going to be present here, and the remaining charge will be automatically repelled at this collector region, right? So this is how concentration is going to affect. Now when it comes to the size, right, when it comes to the size, right, so as collector is already having its own charges, but now what is happening, whatever the charges coming from this emitter, right, emitter to the collector, so so total number of charges that is going to be present in this collector region are going to increase. So if the number of charges are increased, right, so the current will be much higher in character, right? Number of charges increases. So it may be possible that this collector region may get heated up, right? Because of number of charges are increased in this collector region, and because of this higher current, higher charges, higher current, this collector region can get heated up, right? So if it gets heated up, it can burn out, right? So to reduce that drawback, we have increased this size this of the collector as compared to emitter, right? So that this collector can handle more number of charges, or it can collect more number of charges as compared to this emitter, right? Whatever the charges are going to be emitted by this emitter will be all collected at collector. Even those whatever the minority carriers present on base region, p region, they will be collected at this collector region. If the right, if these all the charges between this base region and the emitter region both added together, and if the region is smaller, whatever the charges coming to this collector region, they will try to occupy this region, right? And if the region or the charges are greater than this collector region, right, so it will definitely damage this collector region or this junction, right, as more number of charges they are increased. So to to have a gradient of those charges, mean they equally distribute those charges within this collector, or to collect properly all those charges, the size must be greater than those both base and emitter joined together, right? So that's why these to collect all those charges, maximum number of charges, the collector size is made large as compared to what emitter, and base width is made small, so that very, very small, so that very less number of means 0.01% of the charges emitted by emitter should be collected at or recombinate at this base region, and remaining charges has to be collected at this or should flow toward this collector region, right? So this is what the construction on symbol of this particular, yeah. Then we have to learn how this device is going to you know can be used as a transistor, right? Means we have to get variation of resistance from low resistance to higher resistance, right? So that have to controlled, you know, with the above controlling this emitter based junction and collector based junction, right? Because these are the two PN junction. So we are going to apply certain voltages across this base and emitter, this collector and emitter, right? And because of that, we will get certain conditions, and based on the conditions, right, we have certain modes, right, that we will see in next lecture.